I just say something very quickly? If people who come late, maybe, if you want your slides to be on this machine, please send them to me by email at this email address. Just any time, or at least before the end of the break, just before the session in which your talk is in. Unlike Alexandra, who sends them during the talk.
Next speaker, Alexandra, Automata learning and technical perspective as a trigger for Prakash Panangaden.
I did send that before, but I found it like. Anyway, so Prakash, it's an honor to be here today, giving this talk in this workshop. That, as you see, many people are here for you, and that says a lot. Quoting Frank, this will be a simple talk, and I hope to get everyone to lunch on time. I want to give you a glimpse of what I've been recently doing on automata learning, which is something I got inspired by you. But before I go on the technical part, I have some personal words of thanks. While I was preparing for this talk, I thought a bit about when we met. And, let me see if this works.
What have you scraped out of Facebook?
So all these pictures are personal pictures, not from Facebook. We met many years ago at Calco, and I was a terrified student then. And this is a picture of your invited talk at Calco that year. And after my talk, you got up and you asked lots of questions, and I had no answer to any of them. And the only thing I could think at that time was, how did this guy understood the work I did in a couple of years in 20 minutes, and is asking questions that never crossed my mind. So I was very terrified. After a couple of hours, you walked up to me and you said, "Hi, I'm Prakash Panangaden. I've been reviewing all your papers." And I was even more terrified. What was really, in that conference, but also later along the years, what was clear to me is that you care a lot about young researchers and about the work we do, and you help us a lot in our careers, and I'm very grateful for that, and I know other people here in the audience, I'm looking at Mateo. I know other people here in the audience who are also very, very grateful for all the help you give us. So that's one of your many, many talents and qualities. The year after, you invited me to a workshop, a great workshop in Barbados. This is during, I think this is during
This doesn't look natural.
I was less terrified. And also during that workshop we became co-authors, and here's us, you wearing your thinking cap. And also that year I became your sous chef when you decided to cook a magnificent meal for 30 people during Dexter's 60th birthday. So here we are at Dexter's kitchen with the result of the work of a couple of hours. We also did some exploring of PowerPoint together, and this year we co-organized the Barbados workshop, which was very nice. So it's been a wonderful journey. The last thing I want to mention, and it goes back to a remark that Mike made yesterday during his introduction to the workshop, is that you do a lot for the community, and we do appreciate that. And I think the latest example is the creation of SIGLOC, which is an ACM special interest group in logic. And this was the result of many people's work behind the scenes and many years working for this. And you're the driving force behind it, so thanks a lot, Prakash. And if anyone wants to give Prakash a birthday present, please register for a SIGLOC. And this brought us to another level of our professional relationship, because I'm now your secretary.
Not quite
talk on automata learning. So this is how I came to know about automata learning. In 2011, I moved to Nijmegen, where I met Chris Panangaden, and he mentioned to me, you like automata. There's this paper by Dana Anglin on automata learning. I think you should read it. So I printed the paper then. Then one night in Dagstoel, the year after, I don't know if you remember where we were during this conversation.
Yes, I do.
So Clemens probably also remembers. But so we were having a nice conversation in Dagstoel, and you said, I have this feeling that category theory has something to say about automata learning. So I came back from Dagstoel, and I printed the paper again. Then in 2013, we were putting together a volume, and I wanted to write a paper for your volume. So I printed the paper again, but this time I actually read it, and with your advice, with categorical classes, and this is joint work with Bart Jacobs. So for the rest of the talk, I'm going to tell you a little bit about what we did and about the algorithm in this paper. So it's basically a categorical rephrasing of the algorithm in Anglin's original paper, and showing that, as usual, you were right. So let me explain you what are the ingredients of this, what Anglin calls the L-star algorithm. So there is what Bart and I actually coined this term master language. But there's a language, a regular language, let's call it L, that you don't know this language, but you want to learn it. And in order to learn it, you are given a so-called teacher who knows the language and can answer two types of questions. You can ask the teacher, is the word in the language? And once you think you have enough information to make a guess about this language that you want to learn, you can ask the teacher, is my guess correct? And the teacher will either say, yes, it's correct, or it will say, no, it's not correct, and will give you back a counterexample, so a word that was supposed to be in the language that is not. This is an algorithm that Anglin devised in 1987. And the crucial ingredient in this algorithm is what she calls an observation table. So the algorithm actually incrementally builds this observation table, which gets refined. And once this table has two properties, which properties are called closed and persistent, I'll explain this in a second, you can build a finite automaton hopefully accepting L, and this automaton is minimal. So let's start by clarifying what is an observation table and what are those properties of closed and consistency. So an observation table is a table which is indexed by, so the rows and the columns are indexed by words. So we have two sets of words, S and E, and the table is just a function from, so we have S, and so this is S concatenated with A, so we have a set of words, and all those words extended by a letter A. So A is the alphabet over which the language you want to learn is defined. And the columns are indexed by words in E, and then the entries of the table are just 0 or 1. And an entry in this table, so if row of some word, this word in S, and some other word in E is 1 if and only if the word W is in the language. So this table is built with the knowledge of the language you're trying to learn, and you fill in the table, so you fill in the zeros or ones based on queries you ask to the teacher, basically. And then a table is said to be closed if for all words in this S.A set, so think of so S is a set of words, and then S.A are the words with one more letter. So if for all rows in that table, for indexed by words from this set, there already exists a word in the set S, such that the row, the new row, was already there. Okay? So this means that the information that the words of S with an extra letter add to the table is non-existent. So the table was already closed. That's why it's called closed. A table is consistent if whenever you look at two rows indexed by words in S, and those two rows are equal, then after you extend the word with one letter for all letters, the rows you build are still equal. Okay? So this is the property of being consistent. And so we read these properties and we puzzled looking at them for a while and tried to understand what this means categorically. And here is how the formulation we came up with. So what does exactly close say? Okay, we have a table, and this table basically has two parts. So you can think of this table as having here some words. This is the set E, and then you have here some words, some other words, and this is the set S and the set S dot A. So if we break the table down as having these two parts, then what the property of closed is saying is, okay, so you have this table, this part of the table that only contains the rows of S. You look at how many different rows you have in there. So you look at the image factorization of this map, and this gives you all the distinct rows that you have here, because there might be rows here that are the same. And you do the same for the other part of the table, so the table with S dot A. And if the table is closed, this is saying that every row in S dot A has a corresponding representative in S. So there must exist a map that sends any row in S dot A to a row in S. And this map, if it exists, is unique. So this is kind of a simple observation. But what makes this observation rather nice, in my view, is that now if you look at consistency, what is consistency really saying? And you try to puzzle a bit about it. And here is what consistency is saying. So consistency is saying, okay, take two elements in S, okay, we have the table with the elements indexed by A, and it says if two rows are identified already in S, so you look again at the image factorization of the table and you have the rows, and it's saying if two things are already identified here, so if they are mapped to the same element here, then they are also mapped to the same element after you extend these elements with another letter. So if you look at the curried version of this map, so that you extract this A, so that you get for all A, this means that if two things are identified here, they are also identified here. So there exists a map here that maps the rows that were identified here to the rows that are identified here. And again, if this map exists, it is unique. So having this in one slide somehow gives this beautiful picture that is very symmetric. And so Bart and I were very pleased with this rephrasing. And so this is basically just a categorical interpretation of Angewin's definition. And then you can show that indeed this corresponds exactly to what she defined. And once you have the table, the closed and consistent table, you can build an automaton. And here is how Angewin defines this automaton in her paper. So the states in this automaton are the rows in the table indexed by S. So she looks at takes all the rows, and these rows are the states. The set of final states are all rows in this table that have a 1 in the lambda column. So if there is a 1 there, then this will be a final state. The initial state is the row of the empty word. So lambda is the empty word, I should have said this before. And the transition function of this automaton is built in the following way. If you're given a state, that is a row, and a letter, then the next state is just a row of S dot. So S concatenated with A. And I'm not going to go into details here in view of time, but the well-definedness of this automaton uses the fact that the table is closed and consistent. That's why we need those properties. Now, so we also looked at this and tried to understand what it meant categorically. And I want to show you how the transition function can be defined. I'm going to do this in the whiteboard because I need these two pictures. So the table is closed and consistent, and we can use that information to build the transition function. And the transition function is a function from the set of states to so for every state and every letter you get a new state. So we would like to build here a function delta. It will become clear in a second why I'm drawing things this way. And what do we have to build this? Well, we have a table, and we know that these two diagrams are valid for this table. So how can we do it? Okay, so we know that we have here, so Q here is basically that bullet there. And we know we have here this map E, which is an epi. And we know that we can build a map from Q to 2 to the E, the A, namely this map. Okay? So we have here a map, let's call it, I don't know what I call it in the other slide, let's hope it was sine. And this map is M composed with J. And here I have a map, namely M A. And now probably you'll see where I'm going. If I would have a map here, let's call it phi, then I know that delta exists and is unique by the diagonal filling property, and such phi exists by using, so I've used here J, and now as you can imagine, I will use I here to make it, to fill in the whole thing. Here we go, yes, we called it psi, and this is the map that you get, which is a curved version of I composed with E. So we can get nicely the transition function using this property. That's kind of neat as well. And if we put everything together, the automaton that we built from a table can be captured in this nice diagram that again looks like a butterfly, going back to Jan's talk yesterday, where the initial state is the row of the empty word, and the final state is just evaluating that the rows in the column for the empty word. That's what this map does. And the delta is defined as I just explained. And now what is also nice, and going back to other work by Prakash and several people, and that was mentioned by Jan yesterday, is that the proof of minimality of this automaton that we built, because it was part of Anglewin's paper, that the automaton, this automaton that we built now associated with a closed and consistent table is minimal, in order to prove that, we find back, we call it here the usual butterfly, but we find back the butterfly picture that Jan yesterday used in his talk, and that Prakash and others have found back in Jozowski's minimization algorithm. And so it was also very pleasing to see the connection with previous work of Prakash and others. So that's nice. So we have also a categorical proof of minimality. And now I want to show you the algorithm, but the output fits in one slide. This is just what I want to show you because I'm going to show it to you by example. I'm not going to read line by line the algorithm. So here's how the algorithm works. Let's imagine we start with this master language. The language of words where the number of A's is divisible by 3. Okay, so the initial table, let me just show you the first line of the algorithm. So the table starts to be built just with S being the empty word and B the empty word. So the initial table we build just checks, so asks the teacher the question, is the empty word in this language? And the teacher says yes. Okay, so I put a 1 there. Then I extend this with one letter and I ask the teacher, is the word A in the language? She says no. I don't know why I'm calling the teacher she, but never mind. So the teacher says no, and okay, you put a 0 there. Then you ask, is B in the language? And the teacher says yes, so you put a 1 there. And then you ask, is this table consistent? And since there's only one row here in the S part, it is trivially consistent. But is it closed? And the answer is no. Why? Because we have this row here, the row for A, that is a 0, it's this cell with 0, and that's not represented here. So what happens when the table is not closed? The algorithm says, if the table is not closed, you just basically find the row which is not yet represented there, and you add it to S. So you extend S with the word that was not yet represented there. So in this case, that would be this row indexed by A. So we extend S with A, and we have now this table. So we extended S with A, we have 2 rows in the S part, and we build the rest of the table again by querying the teacher, is word AA in the table, is word AD in the table. And we go on, and now in this table we can check, and it's both closed and consistent. So we make a guess. And we make a guess. So we take, so this has 2 states. These are the 2 rows here. The row of lambda and the row of A. And if you check the transitions, okay, so the row of lambda with an A makes a transition to the row of A, which is this Q1. The row of lambda with a B makes a transition to the row of P, which is this cell with a 1, which is precisely represented by the row of lambda, so hence this loop here. And you fill in all the transitions in this automaton, and this is your guess, which is wrong. So the teacher says it's wrong, and replies with counterexample AAA, which should be accepted in the language L, but it's not accepted by our automaton. So the automaton, if you run word AAA, it's not accepted. So what do we do to the counterexamples? How do we process counterexamples? So if the teacher replies with a counterexample, we again have to extend the table. So we add this counterexample to the table, but we also add all its prefixes. So in this case, we extend the table with the words A, AA, AAA. A was already there, but the other 2 were not. So here's what we get. And then, unfortunately, extending it in this way makes the table non-consistent. And why is that? We have 2 rows here which are the same, A and AA. And if we now extend this with one more A, we go from here we go here, and from here we go here, and those rows will now be distinguished. So this is a problem because the table is not consistent, and the algorithm says when the table is not consistent, you have to extend now the column index in order to make sure that you distinguish these two rows. So in other words, in this case, if we extend the column index with an A, what will happen is the following. These two rows, which before, these two rows here, which...
Alexandra,
yeah. Okay, yeah, I'm about to finish. I'm about to jump to the conclusion, please. These two rows here, which before were the same, A and AA, now are different. So they won't play a role in the consistency chain. And therefore, after we do this, this table happens to be closed and consistent, and we can take a second guess. And this time, this will have 3 states, and note now that S has actually 4 elements, but there are 2 rows here which are the same, the row for lambda and the row for AAA. So the automaton will have 3 states, and if you fill in the transitions and everything, this automaton now indeed accepts the language of words that contain, the number of A's that they contain is divisible by 3, you see this loop. And so the teacher replies, yes. So this is quite, for me, when I read about this algorithm, I was quite surprised that it worked to start with, but also that it produced a minimal automaton. And understanding how this worked categorically was somehow insightful to understand why the produced automaton was minimal and why indeed the algorithm terminated. So once we understood it categorically, without actually much effort, we observed that everything, so the table, the automaton, the proof of minimality, this all was independent of the output set. So we could immediately generalize from deterministic automata to Moore and Mealy machines, which are automata with outputs, and then the language becomes let's say a generalized language or a weighted language, which are formal power series. So it assigns words to an output set, and this output set can be unstructured, or it can also be a semi-ring or a field. And so this led us to an algorithm for Moore and Mealy machines. And then we also observed that categorically the only thing we needed was a category with factorization structure, and therefore we could also do this, for instance, in vector spaces, and we have an algorithm for linear weighted automata, which Prakash also likes very much, so we were also very pleased by this, and you can find all these examples in the paper. So I come to the conclusion. This was kind of a trivial exercise, you could say, this reinterpretation categorically, but for us it was quite insightful, so maybe people appreciate this. And the Mealy example, one thing I wanted to say is that there are several papers justifying why the algorithm for Mealy machines works, but the categorical view in the algorithm really just gives you this for free, which was very, very pleasing as well. The applications of learning are vast, and there's a rich playground where I think we could give some, so where category theory could play a role. And there's a lot of examples, and we are now looking at learning from incomplete information, also heuristics. I'm looking with a student and how to understand certain heuristics that you find in these more practical papers categorically. And we've actually found a mistake in a paper by understanding it categorically, and we wrote to the authors, and we are now trying to fix it using the category theory. So that would be very nice if that turns out to work. So Prakash, category theory does have something to say about learning, so thanks for the tip and for the inspiration, and happy birthday.
That was lovely, and it worked out just as I hoped, so thanks for doing this.
Questions?
So you have these, you started with Angolan's algorithm and then you generalized to other cases. But your examples are all on words, so do you think this approach can work for tree automata? Or, I mean, automaton all on words.
That's a tough one. Okay, I'm going to give you a cryptic answer. If you can show that the semantics of this automata works by final Paul algebra, then probably it will work. But the problem is, for tree automata, this has not yet been understood. We made an attempt a couple of years ago. I'm now looking at part of this movie. And we were not very successful. But I won't say no. I mean, it could work.
Other questions?
Thanks very much.